Can you see the screen?
Yes, doctor.
Okay, so let's start. There are a few more students need to join. I don't know when they will join. Maybe I will wait for 2 minutes.
Mister,
Yes,
can you see if I submitted the assignment?
you cannot check on your
No,
side.
it's not written that I submitted the assignment.
Wait, let me check. Where is the card book? Yeah, can you see your marks, Ajir?
Yes.
You cannot see by your on your side. You cannot see.
No, it's written that it's not submitted.
Okay. Quiz. There are some settings I think I need to change later on. Then I will show you the marks of the quiz also. You can see it here also, but I want to see on your side that everybody can see but their own marks only. Okay, because here you can see everybody else marks also. Okay, not only yours, you can also see other marks. So I don't want that one. Okay, so maybe later on I will share. I will try to see the settings of the quiz. Then I think you will be able to see the marks of the quiz also. Okay, so let's start with today's topic. I hope you have done the previous homework. Okay, many of you are. I don't know why you are not submitting your homework. If you are not submitting your homework, then you understand what are the consequences of this not submission. Okay, so make sure you submit your work. This is very very important. Okay. Okay, because if I try to help you later on in grading, or if you need any marks later on to upgrade your grade, then if you don't submit your homework on time, so it means like you are not what you can say, you are not serious about this studies. Okay, so then I will not help you in that case. If you up if you upload your marks, your assignments, upload your homework on time, then I can imagine that you are serious about this course. Okay, then I can help you in that in the future also. Okay, maybe if you need any help uh, in terms of upgrading your grade, if you need some marks, few marks, then I can help you in that way. But if you don't listen to me, then you will have some problem. Okay, right, so let me start with today's topic. So today we will talk about absorption. Okay, so absorption, normally we will do, there are two phenomena in chemical engineering, and I think you probably heard of one is called adsorption, another one is called absorption. Let me open whiteboard. So this is chemical medical analysis. It's taking down. Okay, find some empty place. We can I write? looks like that I write too much. Okay, so basically there are two phenomena. One is absorption, and the second one is adsorption. So in absorption, what we are doing, we are using gases. We have gases, okay, and we will use some solvents, okay, to absorb those gases. For example, in case of let's say you have methane and carbon dioxide, and you don't want carbon dioxide. You know that this carbon dioxide is one of the acid gases, okay. So these gases will cause problem later on in the process industry. So you don't want this acid gas to go forward to the process industry. So you want to minimize that content. You cannot completely remove it, but you can minimize that content. So the way you can minimize the content is you basically mix this mixture with some kind of a solvent. Okay, that solvent, the choice of the solvent depends what kind of which component you want to absorb from this mixture. Okay, so for example, if you're taking water, water can absorb carbon dioxide, but it cannot absorb methane. Okay, so if you're taking water as a solvent, so what happened when you mix this component? So when this gas is mixed with water, they will absorb carbon dioxide from this water, not like fully, but some amount of the carbon dioxide is absorbed in water. So at the exit, you will get uh, more of methane and very small amount of carbon dioxide. Okay, so this is what you are trying to do. Basically, you are trying to separate the carbon dioxide content from this mixture by using a solvent. This process is called absorption, where you're absorbing some gas in a solvent. Okay, this is absorption. What's this? Okay, so absorption, what we will do in absorption, we are basically absorbing the gas, the one which we want to absorb by using a solvent. Okay, so this phenomena is absorption phenomena, and this is mostly, you can say, we have all these phenomena are normally not chemical in nature, they are physical in nature. Okay, in adsorption, what we are doing basically, for example, if you have the gases, you use some kind of a solid. Okay, solid. And what happened, some of these gases, for example, if you have methane and you have carbon dioxide, and this, in this mixture, these two gases, carbon dioxide and this solid that we are using, this solid has the affinity, has the tendency to absorb or adsorb carbon dioxide on the top. So when you are passing this mixture through this solid, what happened, this carbon dioxide particles will stay on the top or stay on the surface of this solid. Okay, so they are physically adsorbing on the surface of the solid. And when it is go out, what you will get, only pure methane. Okay, not 100% pure, but you have small amount of carbon dioxide still there, but the idea is you will, majority of carbon dioxide you are basically adsorbing on the surface of this solid. So this process where you are physically adsorbing or removing carbon dioxide using a solid, that is called adsorption. Okay, in this absorption you are using a liquid to absorb a gas, but in case of adsorption you are using a solid to adsorb, physically adsorb the gas from the mixture, from which one you want to absorb. Okay, so this is the difference between adsorption and absorption. So today's lecture, what we talk about absorption. So we are basically using the first one, which we are using a solvent to absorb the gas which we want to remove. Okay, so this chapter introduced the use of Aspen HYSYS to model a continuous gas absorption process in a packed column. So normally when you talk about absorption, absorptions are happening in a packed column. Okay, so you have something like a column, like a distillation column, but distillation column have trays. This one don't have a trays, they have some kind of a packing inside the column. Okay, that's why it is a pack column. You can also use trays in the in the absorption, but mostly they will use uh, the particles, or packing inside the column. And did you know why we are using a packing? What is the benefit of using a packing?
to increase the surface area for contact.
Yeah, to increase the surface area, to
More
increase
contact.
the mass and heat transfer. Okay,
Yes.
so if you use packing, then you will increase mass and heat transfer. And obviously, this packing, you have different types of packing available. Okay, there are some are ceramic in nature, ceramic packings. Some are glass. Okay, some are metal. So depending on what kind of component we are removing, we will change, or we will use that particular packing. Okay, so in absorption, what is happening? You have a gases. Okay, for example, here you can have methane plus carbon dioxide, and for example, here on the top, we use gases on the bottom, and we will use, let's say, I use water on the top. Okay, why we are not using water here and gases here? Why the gases is coming from the bottom and the water is coming from the top?
Because gas is less density, can go
Yeah,
upward.
gas is less density and they can easily go up. Okay,
Yes,
against, and the water, they basically come down by using a gravity. So that is the reason why we're using water on the top and gases on the bottom. So what happened when the gas mixture will go up? They go through those packings, and the water, when they shower on the top, and when they go through those packings, there's exchange between the water and the gases inside the column. Okay, so when there's exchange happening, what happened? The carbon dioxide, they can absorb in water, but methane cannot. So what happened when the they go up? Here you will only get methane, not 100%, but you will definitely get high amount of methane, and a small amount of carbon dioxide which cannot be able to absorb in the water will be removed on the top. So this water, when they come out from here, this water contains water plus carbon dioxide. Okay, so this is an acid water. This water is pure water. This is acid water because the carbon dioxide is absorbed in water, so that's why it is acidic water. And here, what you use, basically using a different type of packing and using a phenomena of absorption. This is absorption phenomena. Okay, so what you are doing here, basically using a process of absorption to remove carbon dioxide from this mixture, or reduce the amount of carbon dioxide from the mixture by using a water. Obviously, water is not a very good solvent for carbon dioxide. We will use different types of solvent. The most important solvent which is industrially used is MEA, methyl ethyl amines. Okay, amines or any type of amines. Amines we can normally use instead of water to remove the carbon dioxide, or if you have any other gas from the mixture. For example, normally we use amines for removal of carbon dioxide and hydrogen sulfide. Okay, mostly for hydrogen sulfide, because carbon dioxide is not as dangerous as hydrogen sulfide because of the sulfur content. Okay, so this is more problematic later on as compared to carbon dioxide. So this is what the absorption phenomena is. Okay, and this is what we are going to simulate inside Aspen HYSYS. So let me start Aspen HYSYS also. I think I closed that one. Okay, so what we are doing, basically, the only unit operation of contained in the absorber is the tray section. So we have two types of columns absorption. Okay, one is tray types where we use the trays, and the other one is pack column. We will use packing instead of trays. And the only streams that is overhead vapor, and the bottom is the liquid product. So we get two products. One is on the top, which contains a high amount of which is our main product, and one on the bottom which contains the liquid which absorbs the gas that we want to absorb. Okay, so there is no available specification. Specification means we don't have the idea how much is the height, how much is the diameter of the absorber. Okay, this one we can obtain using the information that we will give to the absorber. Okay, based on our information, like what is the flow rate, what is the component, everything, we have the inside Aspen HYSYS we have the ability to find out the diameter of the absorber, which is the base case for all tower configurations. Okay, the condition and the composition of the column feed stream, as well as the operating pressure, define the resulting converge. This is the important thing regarding absorption. In order for the absorption to run perfectly, you need to provide, it must understand that the condition that you're providing and the composition of the feed stream that you're providing and the operating pressure that you're providing, this will help the absorption to converge. Okay, if you change any of those settings, this will affect your result. Okay, so you make sure your results, you use the settings or use the conditions that will perfectly match and that will help the absorption column to converge. Okay, I will talk about this one later on, but normally if you are working with the absorption column for a big plant, then obviously these information play a very important role. Okay, if you change any of those compositions or any of those conditions, then you cannot get the converged solution. Okay, the converged solution includes the conditions. Okay, condition means temperature, pressure, flow rates, and the composition of your streams. Okay, so when the solution is converged, they will give you the required information for temperature, pressure, conditions, and other properties, physical thermophysical properties. Plus, they also give you the composition of vapor and liquid stream. This is what you are seeking basically. If you look at your tower, what you are looking for in this case is what is the composition of methane and carbon dioxide which you are getting on the top of the column, absorption column, and what is the composition of your liquid stream which contains carbon dioxide on the bottom of the column. So this is what your main goal is. Plus, your main goal also to find out what is the diameter of the column. In some cases, you can also use this one to find out the height of the column. Okay, specification, these are specification. And if you know the diameter and the height, you can also get the cross-sectional area. But cross-sectional area is not as much important as this diameter and height is important. But if you look at this column also, the height includes the packing height, okay, plus the height that you're leaving on the top and on the bottom. Okay, so there's a different height. The height of the column is different, and the packing height is different. Okay, we talk about this one also, and probably in the later on, if you are choosing a graduation project, might be if you choose plant design 1 and 2, you are able to find the height of the column. Okay, but in Aspen HYSYS we can also have we can also find out the height. We don't have to do much calculation in Aspen HYSYS, but we can get the information straight away. Okay, the only thing we need to provide in Aspen HYSYS is what kind of packing we are using. Okay, either we are using a ceramic packing, glass packing, or metal packing. Okay, that is depending on what kind of packing we are using. Okay, let's go back to the question. So the question that we have here, by the end of this exercise, you are able to use the absorption column in Aspen HYSYS, okay? And you understand the absorption process. Similarly, you can also find out the design parameter of the column, like diameter and height of the column, which we can also do in this course, in this lecture also. So the question that you have is carbon dioxide is absorbed in propylene. So you look at here. In the information I mentioned here, I use water, right? But instead of water, we use propylene carbonate as a solvent that can absorb carbon dioxide. The inlet gas stream contains 20% of carbon dioxide and 80% of methane. So we have 20% carbon dioxide, which is a very high amount. Okay, this amount we need to reduce. And we also have the methane, which is 80%. This gas stream is mixed or is being mixed with this solvent in order to remove the carbon dioxide, not fully, but at least reduce the amount. The gas stream flow rate flows at the rate of 2 meter cube per second. Here you can see we are given the flow rate, but not in terms of gram mole or not in terms of kg mole. Or okay, we are given the flow rate as a volumetric flow rate, because the units are meter cube per second. So make sure you use the proper units in Aspen HYSYS. And the column operates at 60 degrees Celsius. So the column is operating means like the temperature of the column here, wherever it is 60 degrees Celsius. Okay, and the pressure also on the column doesn't matter here, doesn't matter here, doesn't matter here. The pressure also is operating at 60.1 atmospheric. This is the information regarding the column. Okay, and also this information is also for the feed also. Okay, the inlet solvent. Now the solvent is flowing because we are working with two inlet streams and two outlet streams. So we need to know what is the flow rate of the solvent entering, what is the flow rate of the gas that is entering. Okay, so the inlet solvent is entering at 2000 kg mole per hour. Solvent is entering at this flow rate, which is in kg mole per hour, whereas the gas entering as volumetric flow rate, which is 2 meter cube per second. You need to use Aspen HYSYS to find out what is the concentration of CO2 in the exit stream. Means what is the concentration of this carbon dioxide here on the top. This is what you need to find out. Also, once you finish this one, then you need to find out what is the column height and what is the column diameter. These two information also you need to find out, and these two informations are the specifications of the column. Okay, based on your statement that is given to you, you need to find out what is the height and what is the column diameter. So in this particular example, what we need to do, we need to use a different kind of equation of state that is not pure Ping Robinson, but that is called sour Ping Robinson. Sour is normally use the terms, when we use the term sour, it means they contain hydrogen sulfide plus CO2. So any one of them, if they are present, then the gas become sour. Okay, if you remove those gases, then the gas become sweet gas. Okay, so we have the component methane, we have carbon dioxide, and we have the solvent, which is propylene carbonate. Okay, you might find some difficulty finding this component, but try to use either the formula or the name properly to find out this component. I will show you in case of if you're facing difficulty, then I will write the formula also by using a formula which is shown here. You can easily find this component in Aspen HYSYS. Okay, so I will put uh, this in separate window and Aspen HYSYS on the separate window so I can see both windows together. Let me find out the component first. So the first thing we need to do, we need to go to a new simulation and we need to select the components. So it will take some time to open. Okay, so we need to go to add components, and we have three components that we need to add. One is methane. Okay, that we need to add. Second one is carbon dioxide, and the third one is I will first check with the name. Is it searching properly? Propylene. Carbon. You can see here we have many components with propylene, right? So that is the reason why it is showing a problem. So let me check with like this. We can find it. So you don't need to put the space between the components. If you write propylene, no need to put space. Just write carbonate, CAR. You can find the component. You can also find in terms of the formula. For example, the formula for this one is C3. But we cannot, it's difficult for us to put is equal to, okay, we can put this one. So you can see here we have the component which is shown here. So either you can search with a formula or you can search with the name. If you're searching with the name, make sure you don't put space between them. Okay, just write like this, you can find out the component. Okay, so in the exam, if you might face the difficulty. So this is how you can search the components, either by name or by formula. Okay, the fluid package that we are going to add in this case is sour PR. It's a kind of Pung Robinson, but it is purely used for gases which contain carbon dioxide or hydrogen sulfide. In our case, we have carbon dioxide, so we will use sour Ping Robinson instead of Ping Robinson. Okay, this is a kind of Ping Robinson equation of state, but it is mostly used for acid gases. Okay, so in this case, we have acid gas, which is carbon dioxide, so you choose sour Ping Robinson. Then you need to go to simulation environment. We don't have any reaction in our system, so we don't go to the reaction tab. We only go to the components tab and also the fluid package. Now we need to add two feed components. There's two ways to do this. Either you can create the material stream and then go to the absorption, or you can go directly to absorption and then add a material stream. The easy way is to you can select the absorber and then you can type in the information for the feed in. Okay, so what I will do, I will go and find out what is the. So I will go to separators, and if you look at here on your screen, you can have many different separators. Okay, the one you need to know, which you need to find out, is containing two inputs and two exits. Okay, so if you look at here on this one, if you just scroll it on top, you can see we have it shows the name also, that this is absorber. Absorber has two inputs and two outputs. Similarly, we have another kind of absorber, which is known as liquid extractor. They also have two inputs and two outputs. This one is not the one which we are studying right now. Okay, which we maybe we will talk about this one in the future, but not now. The one which we need to select, they have two arrows in and two arrows out. Okay, and also they show you the name. So you select that one and put it in the center. Then what you need to know, I need to close this one because I need some space. So I will double click and open. You can get this window. Okay, so here you need to specify the information regarding the name of the streams that is going in, the name of the column, and how many trays they have. Initially we will start with the trays. Okay, then we will convert this one into a column, into a pack column. First we will start with the trays. So the first thing you can see on your screen is this column, which have a stages. Stages means trays, and by default they give you the stages numbers are 10. So we will keep this 10 as it is. We don't change this one. Okay, we can change later on if you're using something. If you're working on a big plant, then obviously you can work with these number of stages. But in our case, we will keep it as a default, which is 10. On top stage inlet, so what is entering on the top is solvent. So we can call this one solvent in, and then press enter. Okay, similarly on the bottom stage inlet, I can say we have the gases in, so I can call this one gases in. Similarly, on the solvent outside, I can call this one gases out. Solvent is not entering, coming out from the top, it's coming from the bottom. So gases coming out from the top is gases out, and solvent that is coming out from the bottom is not solvent anymore because they absorb the gas, so this is called liquid out. Okay, you can call with any other name also, but I can call it with this name. Now you can see on your screen we have the option called next that is appear. Okay, so you click on the next icon and click to the next stage. Now if you remember, in the question says that the column is operating at 60.1 atmospheric. So this is the top stage pressure and the bottom stage pressure. So we can call this one 60. The pressure on the top is 60, and same pressure is on the bottom, 60.1 atmospheric. Once you give this information, then you have option called next. Click on the next tab. Now this is the option for the temperature. This is optional. Okay, either you can provide this information or you can leave this information. So in my case, I have this information that is given in our problem statement, that is 60 degrees Celsius. So I can provide this information instead of just leaving it like this. Okay. So the idea is to provide as much information as possible to make the degree of freedom 0. Okay. Now, if you can see, if you have any side streams from this absorption column, then you can go to the side operation. Okay. Otherwise, at this stage, you have all the information that is completely given to you. So you need to click on the done button. Click on done. So it is done. But it is not converged yet because the information regarding the composition, the temperature of the solvent in and the gases in is still, you did not provide that information. So you need to provide that particular information. So you can either close this one or go one by one to these streams and provide this information, or you can just go up to your worksheet, which is shown on the top here. Click on this worksheet. Now you have the information for the solvent in and also for the gases in. So all you need to know is you need to provide this information that is given to you here. So let's talk about solvent in. So in solvent in, I have the temperature which is 60 degrees Celsius. Okay. Similarly, I have the pressure for solvent in, which is 60.1 atmospheric, and the flow rate is in kg mole per hour, which is 2000 kg mole per hour. Okay, for gases in, I have the similar information for temperature and pressure, but the flow rate is different, and it is volumetric flow rate. The temperature is 60, pressure is 60.1, and your flow rate, that is, if you go up, your flow rate is given in terms of 2 meter cube per second. So what we did here, I convert the second into hours. Okay, second is a very small unit to measure, so that's why you always use hours. Okay, flow rate in terms of second is very difficult to measure because second is a very quick unit. Okay, quick time unit. So you need to convert that into hours, meter cube per hour. So what you did basically here, you convert this second into 1 second is equal to 1 hour is equal to 3600 seconds. Okay, so you multiply that one with 3600, so you got the units in terms of hour. So what we need to do, for gas in, I can click here and I can provide that 7200 meter cube per hour for gas in. And for solvent in, I need to know the composition, so I will go to the composition tab. For solvent in, I only have one pure solvent, that is propylene carbonate, so I will put one for propylene carbonate. I click OK because it is in mole fraction, so I click OK. Similarly, for gas in, I have the information for carbon dioxide, methane, which is methane is 80%, so I can call this one 0.8, and carbon dioxide is 20%, which is 0.2. So provide this information, then this is all the information that you need to provide is already you provided the information. Now if you look at here, it is still yellow. Okay, it is not converge. So the way it converges, you need to double click and open this one. Okay, if you open this one here, if you go up here, you can see on the bottom of your window it is saying unconverge, and beside that you have the option to reset and run. This reset is sometimes we use when we give the wrong information here. If you give the wrong information and next time if you change the information, you need to reset it. First you reset it and then run, because we did not change anything yet, we did not run it. So what we need to do, we need to click on the run button. So click on run. So once you click on run, if you provide the information correctly, then immediately it will calculate the mass balance, and immediately it will calculate the energy balance, and it will converge quickly. Okay, how you can get the information that it is converging, you can see here on this screen. If you just close this one, if you go to your Aspen HYSYS window on the bottom, you can see on this part, this is basically what is happening. They are doing iteration and they are finding the error. So the error has to be minimum and it has to be less than 0. Okay, so it is doing this 4 iteration only. With 4 iteration, it is trying to converge, and you can see here the error is going negative 7.519 e raised to power negative 6. Okay, this is converge. Similarly, the heat energy balance is also converge, and the error is also going negative. So it means like both of these with the provided information, both mass balance, both equilibrium information, and the heat energy balance information is converge with only 4 steps. Remember one more thing. Okay, why I'm showing you this one, because later on if you are giving wrong information to absorption, then this part will take long time to converge, not even converge. So if they are doing thousands of iterations and if still they are not converging, it means like the provided information that you give to the absorption is not correct. Okay, so in that case you need to stop the process of conversion, and then you need to reset, change the settings, reset it, and then again you run this one. Okay, then only you are able to uh, what you call do the calculation. Okay, let me find out. I will move it down. So far, if you are able to do the simulation, you will get this result. Okay, this is one part of the question, which is this part up to here. Now up to concentration, you can find out the concentration here by clicking here. You want to know the composition of the exit stream, so you show table for the exit stream of the top. You don't want the flow rates and this information. You only need to know the information of the carbon dioxide. Okay, so again, master component, flow rate, and you want to know the composition of carbon dioxide only. So click here and click done. So if you see here clearly, you can get the flow rate. You can also get the composition. Let me find out the composition. Let me show you the composition also here. So double click, add, again master component, mole flow, mole fraction. Okay, and carbon dioxide mole fraction. You can clearly see we absorb, we have only small amount of carbon dioxide. Obviously, that's the reason why I'm asking you, right? That you are using a different type of solvent, try to absorb the gases. So the gas that we are using here, we use the composition of carbon dioxide 20%. Okay, out of this 20%, only very small amount of carbon dioxide is absorbed in the solvent. And the rest of them will be recovered on the top. This means that the solvent that we are using is not good for absorbing carbon dioxide. So we can change the solvent and we can see how much this will be reduced. Okay, so that is the reason why we use different types of solvents. If you use amines, then you will definitely get a very low number of carbon dioxide here. Okay, obviously this solvent is not good enough. That's why we have a very small amount of carbon dioxide is absorbed and the remaining is removing on the top, which we don't want actually. Okay, we want less amount of carbon dioxide here and more on absorbed on here. Okay, this is what we are looking for. So if you go to the liquid setting, and if you want to show you the information for the liquid, you can clearly see that we are not getting a very high amount of carbon dioxide absorbed here. So I will go to master component, mole fraction. Only carbon dioxide is my concern, so I will click on carbon dioxide and click done. You can clearly see, obviously we have some which is we will only get very small amount of carbon dioxide which is absorbed here, and the rest of them is going or leaving on the top, which we don't want. Technically we don't want the absorption to do like this. So we need to change. We cannot change any other things. What we can change is the solvent. When we change the solvent, then we can check this amount. If this amount is reducing, it means like this solvent is good for capturing or absorbing carbon dioxide. Okay, so this is the first part of your of um, this lecture. The second part, we need to find out what is the column height and column diameter. Okay, now there are two things basically. If you're using previous version, if you're using Aspen HYSYS 8.6, might be 8.8 also, then you don't have a sign like this on the top of the column. You can see there's a small sign like this on the top of this column. This one, you cannot see this column here. Okay, instead you can go to equipment design and you can add a tray sizing here. But if you are working with the new Aspen HYSYS Mini 8.8 or onwards, then definitely you have a sign like this one which is showing on the absorption. So I will show you this one first. Okay, then the other one I will let you know like how you can even go through with the lecture notes and you can find out where the tray sizing are located. Okay, and then you just follow the steps. You can find out the height of the column and the diameter of the column. Okay, but in my case I have this option which is appearing on the top, so I will double click and open this one. This option is basically used to find out the specification of the column, which is means like the height, the diameter, okay, all these, and what type of packing that you have inside the column. So if you open this one, you can see a window like this that will be open. So the first thing you can look at on this window is the column is appearing here. Okay, and there are two stages. One stage starting from the top, first stage, and on the bottom 10th stage. So we have total 10 stages. Okay, so on this side of the window, you can see we have option called Add New. It just means like if you want to have different portions of this column separately designed. For example, this one you want to make it a big diameter. This one you want smaller diameter. This one you have more smaller diameter, or you want the whole column as just one diameter. Okay, you don't want to change into different sections. So in that case, what you need to know, you can see the second option called auto section. This, if you click on this one, they will auto select the whole column. So click on this one. then they will select the whole column, and you can see on your screen it become gray, okay, dark gray. And beside that one, you have also have some information that is shown up here. I will go one by one. So this one is just the name of the column, the section. This whole section is by default the call. You can change this name also, okay, if you want to change, or you will leave it like this also. And it is starting from the main tower from the top, which is the top stray is on the top, and the ending stage is on the bottom, which is the 10th stage. So total stages are 10 stages. Now inside these stages, you have packing or you have trays. So if you click on this one, there's a mode. There are two modes. One mode is that you can either use the interactive sizing option of the Aspen HYSYS. They will basically automatically choose the option, or you can use the rating option, which you manually put the information. Okay, I will keep it as an interactive setting sizing. Then the second option is like either inside the column, do you have the trays or you have packing. So I say I have packing, not trays. So I will change this one into packed. Instead of tray, I will change this one into packed. Similarly, if you go to the tray packing type, now there are different types of packing. You can see here many different types of packing. So the type of packing that we are going to use in our case is shown up here on this window. That will be called. Let me find out the packing for you. Yeah, this one. So the packing type that we are going to use in our case is called rashing ring ceramic. This is a ceramic type of packing, and it is called rashing rings. This is the type of shape that is called rashing rings, and the size of the packing is 1 to 4 inch. So we need to find out this packing. Okay, the first thing we need to find out is what is rashing ring. So we need to see the rashing first. Okay, so click on here and then find out rashing. So you can get the rashing here. So once you click on the rashing, this is being selected. Now this is a generic, so I will keep it as a generic. Okay, that the material of the packing is ceramic. According to my question, the packing is ceramic packing, so I will click this one to a ceramic, not carbon. Okay, carbon means they contain glass or metal or ceramic. Okay, so I will keep it as a ceramic. Now what is the dimension of the packing that I'm looking for? I'm looking for 1 to 4 inch. So I will click here. I will get 1 to 4 inch packing from here. So either it is 1 or 1 to 4. So let's say I can choose 1 inch. Okay, you can choose any other also. So 1 to 4, any type is okay. So I will choose 1 inch packing. Then from here, you can see we have the tray spacing a section pack height. This is empty. The diameter they already calculated here, but you need to click on the view section. Click on the view section, and here you need to specify one information like what is the section pack height. Either you can keep it empty or you can keep it default 0.5 meter. So let's say I will keep it 0.5 meter. So I will keep it like this. Then if you go back uh, to your results, you can clearly see that based on this information that we give, we are getting the high diameter of the column, which is 8.9 meter. Okay, in feet it is 29.43 feet. And the more information you put it here, the more accurate the answer you'll get. But by default, if you are using a small number of information, then obviously this is the information that you're looking for. Okay, you can either click on the view section, you can get this information here, and if you click on the result tab, you can get all the information regarding your column. Okay, regarding the diameter of the column, which is 8.9, the what you call the height, that a pack height. This is a packing height. Okay, not the height of the column, but the height of the section, the whole section of the column is 5 meter. Okay, so this is obviously this one looks like more fatter, not very high. Height is not very much because you can see the diameter is very high as compared to the height, section height. So this is the information that you're looking for, the diameter of the column and the height of the column. So that information that you are seeking, and if you get this information, then you can put this information at the end of this this lecture notes, which here you can put the section diameter, whatever the section diameter, which is 8.969, and what is the section, what is the tray packing height, which is in this case, obviously this is the packing height. Okay, you need to put the height of the full column, so you need to put the extra information. Obviously this basically demands more information to get more accurate data. Okay, accurate information, but roughly this is how you can able to get the height and the diameter. So the height you can write it here, and the composition that you're getting, which is which I showed you before also here, which is 0.19 or means like 19%, that you can write it on this part. This is how you can do absorption and how you can find out the diameter and the height of the column. For those who are using older version of Aspen HYSYS, then for you, you can just follow up this lecture notes. I will share this one with you. Okay, you have a little bit different than normal. So what you need to do is, in this particular case, if you are using an older version, you need to click on this equipment design, and if you click on add, okay, you have an option for tray sizing. Then if you click on the tray sizing, then you can follow up with this window, like this window. Okay, and then you can follow up from here onwards and try to find out what is the height and what is the diameter of the column. Okay, similarly, but the results are almost similar, not very much different, but you can find out the information like this. Okay, so this is how you can find out the specification of the equipment, and also how you can design the absorption column. Okay, so this is regarding this chapter. There's some question which is mentioned here, okay, which I will leave it for you to do. So instead of using 2000 kg mole per hour of the flow rate of the solvent in, if you change this flow rate to 2500 kg mole per hour, then you can run the simulation, and then you can check what is the effect of changing this flow rate of the solvent in to 2500. What is the effect on the composition of carbon dioxide that is leaving on the gases out? Okay, this is your home task. Plus, I also recommend you, I will also give you one more question for you to practice. Okay, I will write it down on this. I have this PowerPoint. I will give you the information for the absorption column here, so you can use this information and use the same method that I just show you here, and find out what is the composition of the gases that is leaving on the top gas out. So let me write down some information that you need. Probably need to run this to do this exercise, so that you are able to do this. For example, the gas in. So for gas in, for example, the components first. Okay, the components that you are using is water. Okay, sulfur dioxide and air. You'll get the component air from directly from Aspen HYSYS. Okay, no need to use. If you cannot get the component air, you can use oxygen and nitrogen separately as a component. Okay, fluid package you use is Ping Robinson, same like normal cases when you use. On liquid in that is coming from the top, you have water. For the gas in that is coming from the bottom, that contains air in. Okay, similarly, you have the gas out, that is pure air, and similarly the liquid that is coming out is called as water out. Now you need to know some information regarding what is the temperature, what is the pressure of the water in and the gas. So water in that is entering, that is obviously pure water. Okay, the temperature of this water in is 20 degrees Celsius. Pressure of this water in is 1 atmospheric, and the flow rate of this water which is entering is 12240 kg mole per hour. Okay, this is the information for the liquid that is coming in. Okay, that is going in, not out. This one has just show you the information, that's why I put the arrow like this. Okay, similarly that air that is coming in, they also contains two components. They also contains carbon sulfur dioxide, which we want to reduce, and the amount of this carbon sulfur dioxide is 0.03. We also have air that is entering, and the amount of air is 0.97. Okay, if you're using, obviously if you're using oxygen and nitrogen, then this composition you cannot put, right? So better to find out the air as a component you can easily find out inside Aspen HYSYS. The conditions for air in is temperature is similar to this one. Water in temperature is 20 degrees Celsius and pressure is 1 atmospheric. Okay, this is the information for, all this information is for gas in. So you have the information for liquid in, you have the information for gas in. What else you need? You have the minimum number of trays which you can use, which is 10. Okay, don't need to change this one. The pressure, this whole column is operating at 1 atmospheric. Okay, so this information you need. So whole column is operating at 1 atmospheric. Temperature, no need because it is optional. So you just avoid the temperature of the whole column. Okay, that you can remove this one. Then simply by putting this information, you run this one and find out what is the composition of that gas that is leaving on the top. Okay, this is one thing. Second, you can do the specification and find out the height and the diameter of the column using this one information, extra information. That is, the packing is called interlocks. This is a type of packing. Okay, like a ceramic packing. Interlocks saddles. You can search it easily there. Okay, and it is a type of ceramic packing. Ceramic packing. Okay, and the size that you are using is 2-inch. Using this information here, find out what is the diameter and what is the height of the column in meters. Okay, in meters. This you need to find out. Okay, this is your question number 1. Yes, anyone have problem?
Doctor, the flow rate of the air in.
Flow rate of air in is 20. Let's say 20 kg mole per hour. Okay, that is the flow rate that you use. This is one question. Similarly, I have another question. Two questions I have for you. Okay, so I want you to get more practice on this one. So that's why I want to give you 2 extra questions. So this is another question. I will share this with you also. Plus, you also get the video, so you can easily get the information from there also. Okay, so you have a similar column. In this column, you have something which is entering, the gas which is entering, and the gas which we are entering here is called air and ammonia. Air ammonia mixture. Okay, air ammonia mixture. That gas that is entering from the bottom is air ammonia mixture, and the composition that you have here. First, I will write down the components that you have. So you have ammonia. Okay, you have air. You have what else you have? You have water, and you have sulfuric acid, which is H2SO4. Okay, so these are the 4 components that you have. Obviously, H2SO4 we are using as a solvent. So in air, we have the component that is entering is air, that is entering as 0.8084. Okay, ammonia, that the composition of ammonia, this is the composition. Okay, ammonia that is entering is 0.1633, and similarly water that is entering is 0.0283. This is the composition of air in mixture. Okay, so we have air, we have ammonia, we have water. The conditions that you require: temperature is 136.5 degrees Celsius, pressure is 202 0.6 kilopascal, and the flow rate is 123.6 kg mole per hour. This is the information for air ammonia mixture. That is the gas that is entering from the bottom. Similarly, for liquid that is entering, which is obviously a sulfuric acid, so you know the sulfuric acid composition, it is 1. Okay, the temperature for the sulfuric acid that is entering is 19 degrees Celsius. Pressure is 1 atmospheric. Okay, that is the only information, and the flow rate that you required for sulfuric acid is 1000 kg mole per hour. That is information for sulfuric acid, and the composition obviously is, we can say this sulfuric acid is not 100% concentrated, that is 98% concentrated. Okay, so in this case we cannot use the composition 1 for sulfuric acid. So if it is 90% concentrated, then it is 98% concentrated, then 2% it is dilute. Okay, so what we means is this H2SO4 is present 0.98 because it is 90% concentrated. You know that the sulfuric acid is present at different concentrations. It is 90%, 95%, 98%. Okay, in our case we are using concentration of sulfuric acid 98%. So 0.98 is sulfuric acid and the remaining is water, which is 0.02. Okay, so this is the composition of liquid in that you are using. We are using 10 number of stages as a default. The top stage pressure is 1 atmospheric. The bottom stage pressure is 2 atmospheric. This one you require. Okay, so I will give you the pressure on the top and the bottom. What else I give you? Nothing. I think this is all information you need to know. And also the temperature, I think that's enough. Yeah, that's I think enough. Yeah, there's another thing that you need to know. The column is operating at 30 degrees Celsius, the temperature on the top, and 30 degrees Celsius on the bottom. Okay, so you have some extra information here. Obviously, using this temperature, using this pressure of the column, using the information that is mentioned for the gas in, using the information for the liquid in, find out what is the composition of gas out, what is the composition of liquid out. Okay, that you need to find out. That's it. Okay, so this one you need to provide me. Okay, so these are the 2 questions that is given to you. I will share this file with you just a moment after the closing this lecture. Okay, so you need to find out the information, complete this simulation, and please submit the simulation also to me. I will give you the link also, just like previous case, to upload your homework. Okay, so finish your simulations. Don't only submit the answers. Okay, please submit your simulations also. Okay, not only your what you called the snapshot is there, but at least you need to put your simulation also. So when I open the simulation, I can see your work. No need to upload the video. Okay, just you need to put your work in terms of snapshot and also in terms of simulation. Both snapshot and simulation you can give it to me on that link. So that's all for today. Okay, did you have any question? You can ask now.
For the second example, Doctor, do we use
Yes.
sour PR or PCR?
Oh, okay. One more thing. Yeah, sorry, I need to mention this one. For this example, you are going to use different question of state. Okay, because you are using a sulfuric acid, and sulfuric acid is acidic in nature. So instead of using Ping-Robinson equation of state in the second example, you need to use NRTL. NRTL you can find out easily. Just search this one. NRTL. This is the equation of state that you use for this simulation. Okay, because because we are using a solvent which is sulfuric acid, and we are also using ammonia and water and we are using 2 different solvents, water and also sulfuric acid. So this is more polar in nature. Okay, so Ping-Robinson equation of state is not giving you the accurate result, so you need to choose the equation of state which can give you the accurate result. So in this case we are using NRTL. Okay, you can easily find out NRTL in the fruit package. Okay, any more questions?
No, it's okay.
Okay. Just use the information. Okay, I will share the file also with you, and please complete the simulation and upload your work. All right.
When do you want it, Doctor?
You can submit today or tomorrow also, no problem. But
Okay.
before the weekend, you need to submit. Okay.
Okay.
Okay. So if you don't have any questions, then thank you very much for listening. If you have any question later on also, you can always welcome to ask. Okay. So thank you very much for listening. You can leave, then I will leave at the end.
All right. Have a good day.
Okay. Take care.